An unsaturated hydrocarbon with a double bond in between the carbon atoms is called an alkene. Alkenes are also called olefins, which means oil forming, as its first member, ethene, on reacting with chlorine, forms an oily substance. As we have studied, a carbon-to-carbon double bond consists of one strong sigma bond and one weak pi bond. A sigma bond is formed due to the head-on overlap between two sp2 hybrid orbitals of two carbon atoms, whereas a pi bond is formed due to the sideways overlap between two pure 2p orbitals of two carbon atoms. Due to the presence of a double bond, an alkene has two hydrogen atoms less than corresponding alkane. Hence, the general molecular formulae of alkenes is CnH2n. The pi bond, which consists of loosely held delocalized pi electrons, serve as a source of electrons for the electron-seeking reagents. Thus, the electron-seeking or electron-deficient reagents, called electrophilic reagents, attack weaker pi bond in alkenes and form corresponding saturated compounds. The presence of the weaker pi bond makes alkenes more reactive than the corresponding alkanes. The IUPAC name of the alkenes can be divided into two parts, that is, root word, which indicates the length of the carbon chain, and suffix -ene, which indicates the double bond. For example, the IUPAC name of an alkene with two carbon atoms can be divided into two parts, that is, root word eth plus the suffix -ene. Hence, the IUPAC name is ethene. In the IUPAC system, alkenes are named by replacing the suffix -ane of the corresponding alkanes by the suffix -ene. For example, ethene is named from ethane by replacing the suffix -ane with -ene. For alkenes with more than 3 carbon atoms, the carbon with a double bond is given the least number, and the number is indicated in the name. For example, but1-ene, but2-ene. An alkane with an alkyl group as a substituent is numbered in such a way that carbon with double bond gets least number. While naming, the number of the carbon atom with the substituent and the name of the substituent, that is alkyl group, is written as a prefix to the name of the parent carbon chain. For example, the following molecules are named as 2-methyl-prop-1-ene, 3-methyl-but-1-ene respectively. In higher alkenes, molecules can be arranged in more than one way. For example, the molecule of alkene with 4 carbon atoms, that is C4H8, can either be arranged as but1-ene, but2-ene, or 2-methyl-prop-1-ene. These are called structural isomers. In addition to this, it is observed that C4H8 shows 2 distinct special arrangements. They are cis-2-butene and trans-2-butene. These are called stereoisomers. Thus, higher alkenes are said to show both structural and stereoisomerism. In structural isomerism, they show chain and position isomerism. In stereoisomerism, they show geometrical or cis-trans isomerism. In a molecule of C4H8, all the carbon atoms are present in the form of straight or branched chains. For example, structures 1 and 2 have straight chains, whereas structure 3 has a branched chain. Structures 1 and 3 and 2 and 3 are said to be chain isomers of each other. When in two structures, the position of the double bond alone is different, they are said to be position isomers. Structures 1 and 2 are position isomers. A compound like but2-ene shows two distinct configurations or spatial arrangements, and hence, its molecules are said to show geometrical isomerism, a type of stereoisomerism. When the two CH3 groups attached to each carbon atom of the double bond are on the same side, the isomer is called a cis isomer. On the other hand, when the two CH3 groups attached to each carbon atom of the double bond are on the opposite side, the isomer is called as trans isomer. Due to the difference in the spatial arrangement, cis and trans isomers have different melting points, boiling points, dipole movement, solubility, and many other properties. For example, the cis but2-ene molecule is polar, whereas the trans but2-ene molecule is non-polar. This is because in a cis but2-ene molecule, as the two CH3 groups are on the same side of the double bond, there is a greater, hence the molecule is polar, CH3 bond dipole on each side, causing distinct positive and negative regions in the molecule. However, in case of a trans but2-ene molecule, the two CH3 groups are present on the opposite sides of the double bond. Thus, the bond dipoles of each CH3 bond cancel each other, making the molecule non-polar. Hence, we can conclude that trans isomers are more stable than cis isomers.